Hello everyone again. As I mentioned, my name is Vincent Britz. I work as a thermal fluid solver developer at Flownex, and today I'm joined by Mark Kynes. Mark is a principal application engineer who specializes in turbo machinery at Ansys. First of all, I would like to take you through the content of our presentation. We will begin with a short introduction where we'll explain the need for a simplified film cooling model, especially for the early design phase. Then we'll give you an overview of the current modeling approaches for film cooling in CFD. This will be followed by an introduction of the new Ansys film cooling model for CFX and Fluent. Then we will discuss the capabilities of Flownex, the one-dimensional network modeling tool, which we are using to predict the internal cooling flow within the vane. Finally, we will take a look at some of the results and comparisons, and we will draw some conclusions. Here I would like to hand over to Mark, who will explain the need for a simplified film cooling model.
Hello from my side as well. So I will start with a question. So why we need a simplified film cooling model? First of all, we add a significant mass flow for cooling within the high pressure turbine stages. This can be up to about 20% of the overall mass flow in the first turbine stage. Therefore, the cooling flow impacts the aerodynamic and thermodynamic performance of the turbine stage. This leads to the need to account for the influence of the film cooling flow as early as possible in the design phase. In addition to that, there is a need for the optimization of the film cooling hose in respect to their numbers, the diameters, and their positions. And for sure, for such a simulation, you wouldn't like to use a model with a mesh which is fully resolved, which means that it resolves the internal cooling flow structures as well as the cooling hose itself, like it is shown on the right-hand side picture here. Therefore, we need a model where the turbine geometry and mesh is separated from the definition of the cooling hose. That means a model where you haven't to mesh or remesh the geometry if you just change, for instance, the cooling hole pattern. This slide shows you the different approaches to model film cooling in CFD. On the left-hand side, there is the resolved model, which is something like the ideal model. All of the inner cooling channels and injection hose are resolved by the mesh itself. This is the most accurate model and allows to account for the conjugate heat transfer, but it isn't practical or just too expensive for the early design phase. In contrast to that, on the right-hand side, you see the most simple model approach. Here, mass flow is just added on source points to represent the cooling hole inlets. The inner cooling channels and its holes happen to be meshed. As just point sources are used, the contribution is limited to a single control volume, which induces a high mesh sensitivity. In addition to that, the point definition is often not easy and not flexible enough for modifying point locations. A solution in between the already mentioned models is the boundary source approach. Here, mass flow is added as a boundary source to represent the cooling hole inlets. This approach is less sensitive to mesh resolution, and expressions can be used to define different hole shapes and injection directions. But these expressions can become very complicated. And finally, details like the injection turbulence can still get wrong because the underlying surface is still treated as a wall. This brings us to a new approach to account for cooling flows, which is named injection region approach. It is somewhere in between the ideal approach and the boundary source approach, as it is a reduced order approach and aims to overcome some limitations and problems of the boundary source approach. For the injection region model, the cooling holes are modeled as virtual or mesh-independent inlets. The model is intended as reduced order approach for the early design phase, whereas it overcomes the drawback of the boundary source approach as the inlets are now true inlets without an underlying wall treatment. The model is fully integrated in Ansys CFX and Fluent, which means it is compatible with all other models. The user can define multiple so-called injection regions for each domain, whereas each injection region consists of multiple hole definitions with the corresponding inflow conditions. The quick and easy definition of the injection regions using expressions, external CSV files, or profiles allows an easy optimization of the number of holes and their positions. and the cooling hose and their inflow directions can be visualized in CFX Pre, as you can see on the picture. Additionally, I would like to mention that the injection region feature is fully applicable to the FMI-FMU interface to support the interaction with a system simulation like Flownex, for instance, for the inner cooling channels. And last but not least, it should be mentioned that the results of the injection region model shows a good agreement with the results of a fully resolved model if the mesh size is comparable. So what does the injection region model offer? It can be used to get the influence of the cooling flow on the aerodynamic performance in the early design phase, for instance, to get the right choke mass flow. And as holes and slots can be defined parametrically, it also allows for an easy optimization. It is also worth to mention that the local coordinate system, for instance, a turbo coordinate system with a span-wise and a stream-wise coordinate between 0 and 1 can be used to define the hole positions. Hence, it is pretty easy to map a certain hole pattern of one blade to another one. And in addition to that, the injection hole angles can be set parametrically based on a local blade surface, which means radial and tangential flow angles can be specified, as you can see on the right lower pictures. But there is still an open question. Where do we get proper boundary conditions for the injection region model? A possible solution is the coupling of a 1D network model with a 3D CFD solver. This is what we did for this presentation. We coupled the 1D network model from Flownex for the internal cooling flow within a high-pressure turbine vane with a 3D CFD simulation of the vane passage flow in Ansys CFX. For the sake of demonstration, we created a reference test case. To reduce the computational effort, the turbine test case has been generated as a linear cascade of a midspan. The geometry of the vane is similar to that of a NASA GE E-Cube engine, and therefore it is typically for the first stage of a high-pressure turbine. The model comprises the fluid region of the passage flow as well as the internal cooling flow and the solid vane. It includes all detailed cooling structures like the cooling holes, the trailing edge cooling slots, as well as the pin-fin cooling. As you can see on the right-hand side picture, the model includes just a small span-wise section of the blade. For the main inlet combustion chamber, outlet conditions were applied. In addition to that, 2 cooling air feeds were included in the models as well. For the final diabatic CFD model, a fully resolved low Reynolds mesh with about 8.2 million cells was generated, and it was solved with Ansys CFX 2023R1, including conjugate heat transfer. In addition to the fully resolved model, a second adiabatic CFD model, which just includes the fluid passage flow, was generated. For this model, the cooling flow is modeled using the injection region model, whereas 2 different boundary condition options were used to provide the inflow conditions of each of the holes and the slots, respectively. Option 1 used the results of the former Ansys CFX simulation of the fully resolved model to set the cooling flow boundary conditions. And for option 2, the boundary conditions were provided by the Flownex 1D network model. To show the influence of the hole resolution on the results, 2 meshes were generated. The first one is a TED prism mesh, whereas all the holes and slot are resolved by the mesh patches. Overall, this mesh comprises about 2.8 million cells. In addition to that, a hex mesh, which is typically used to calculate the aerodynamic performance of the vane, was generated as well. In this mesh, the hole patches are not resolved, and therefore the mesh comprises just 1 million cells. And now I would like to hand over the presentation to Vincent, who will give you more information on the capabilities of Flownex and will explain you how to generate a 1D network model for the internal cooling flow.
Thank you, Mark. Next, I'd like to explain some of the fundamentals of the Flownex tool. Flownex is a one-dimensional modeling tool that uses fundamental physics to model the flow and heat transfer in large systems. Flownex contains a large library of commonly used components and employs advanced fluid models that allows engineers to model complicated systems in a short amount of time. Flownex is also capable of interfacing with many other common engineering tools. It's the integration with Ansys that made today's work possible. Our integration with Ansys includes couplings with CFX, Mechanical, Fluent, Workbench, Twin Builder, as well as compatibility with the FMI interface. As I mentioned, Flownex has a large library of pre-built components that can be used in your simulation models. Looking specifically at gas turbine systems, we have dedicated components that have been developed to be in line with common modeling standards in the gas turbine industry. We have detailed component models for components such as rotating nozzles or rotating orifices. These models include detailed discharge coefficient correlations that include the effect of the shape of the inlet of the nozzle, as well as the length, incidence angle, compressibility effects, and many other effects that are combined to determine a realistic discharge coefficient. We also have components such as a rotating channel that incorporates the body forces on the flow due to the rotation of the machine. These components are designed to capture the pressure drops along the lengths of the channels and can be inclined at arbitrary angles and are ideal for modeling the complex flow passages inside of gas turbine rotors and stators. Flownex also has standard components for modeling common heat transfer paths inside of gas turbine engines. This includes jet impingement convection correlations for modeling the complex flows and heat transfer that result from the need for intense cooling inside of many gas turbine components. We also have correlations for common internal flow structures, such as smooth walls, pedestals, and turbulators that are commonly found inside of the channels of gas turbine blades. Additionally, we have components that can be used to model the other areas of the engines. These include cavities such as rotor-rotor and rotor-stator cavities that exist between the many rotating discs inside of the engine. The cavity models in Flownex capture the complex effects that determine the swirl or the rotational velocity inside of these cavities. These effects include the shape of the rotor and stator walls, the effects of the bolts or any other protrusions into the cavities, as well as effects due to flows entering and exiting the cavities. We also have components that can model the other flow paths inside of the engine, paths that might be rotating gaps between a rotor and a stator. These include incremented friction calculations with the effect of swirl and windage added to the energy equation. We also have detailed labyrinth seal models that are incremented for every single tooth in the seal. These account for choking inside of the seal teeth and include a large number of geometry options. Looking into more detail in the blade modeling space, the flows inside of gas turbine blades can easily be represented through a one-dimensional network. The image on the right there shows a common blade geometry, as Mark mentioned earlier, and as you can see, it can easily be described using a combination of nozzle, passage, and node components. This allows us to accurately represent the various flow paths that exist in the internals of many stator vanes and rotating blades. These components can then be connected to heat transfer components and used to develop a full conjugate heat transfer solution. The details of this simulation are set up as Mark described earlier, using that reduced geometry. For this example, we specifically have to look at two areas of data exchange. The first area is the flow coupling. So this is exchanging the mass flow and temperature from the exiting film cooling hole. That information is then passed into Ansys CFX, and the back pressure, or the pressure on the external of the blade, is then passed as a boundary condition into the one-dimensional simulation in Flownex. On top of that, we also need to make a coupling for a heat transfer connection. This coupling needs to account for the temperature of the fluid inside of the blade, as well as the bulk heat transfer coefficient. These are calculated using the heat transfer components in Flownex and are passed to CFX. CFX then uses this in the heat transfer solution and passes the wall temperature back to Flownex. The data exchange through this is possible through two different techniques with the current implementation in Flownex and CFX. We have either the option to use traditional data exchange through junction box routines, or more recently, we also have the ability to exchange data using the standards set up through the FMI standard. Large models can be combined in Flownex in radial slices. So here on the left-hand side, you can imagine multiple cross-sections in the radial direction being constructed and then layered on top of each other to represent the different radial cross-sections in the blade. These components or these models can include lots of components, and this construction process can be automated through the use of scripting tools such as Python. Flownex has a very detailed and comprehensive API that allows us to automate this process and can significantly speed up the time it takes to build these large system models. On the next slide here, you can see a comparison of the two models. On the left-hand side, we have the Ansys CFX model. This is the fully resolved model, modeling both internal and external flow. And on the right-hand side, we have the Flownex model. The model shows a visual representation of what is being solved in Flownex. In the center, we see these channel components, which represent the flow in the radial direction inside of the cooling channels. And then we see these heat transfer components connected to those channels to capture the heat transfer between the air and the walls of those channels. At radial locations along those channels, you'll see some labels there indicating the actual radial measurement. There are connections to separate drawing pages or separate representations of the model that describe the flows at different radial cross-sections. You can see a representation of one of those cross-sections on the right-hand side. Here we have one of those holes. We refer to these as view nodes. They allow us to connect between drawing pages, but maintain the same node in the solver. And that representation on the right-hand side connects the flow from that channel rather, through a nozzle and out through one of the film cooling holes. Each of those locations in the radial direction where you see one of those labels indicates a location where a radial cross-section is connected. We're not limited to purely radial cross-sections. In the case of inclined holes, it is possible to specify the inclination of the hole as well. However, we've just chosen to represent it this way just for more clarity. Just a reminder what we discussed a few slides earlier. On this model over here on the right-hand side, we're coupling both the flow and heat transfer. So the exit pressures on each of those film cooling holes is the actual pressure value on that boundary condition is passed in through the CFX model, and the wall temperatures for each of the heat transfer components is also specified from the CFX model, keeping that full conjugate heat transfer coupling. If we take a look at some of the results, first looking at the cooling hole mass flow, here in blue, we see the results from Ansys CFX for the fully resolved model. This is with both internal and external flows modeled in a high level of detail with a full mesh. And in orange here, we see the results from Flownex from that internal flow model. We're comparing the mass flows in each of the film cooling holes to see the accuracy of this simplified modeling approach, where we are able to use empirical correlations instead of a fully resolved and fine mesh. Overall, we can see relatively good agreement with the mass flows predicted from Ansys CFX. You can see not only is the trend predicted well, but also the absolute values are predicted well as well. Overall, we see an error of about 0.8% of the total cooling flow. If we look at temperatures, you can see these are film cooling hole exit temperatures. Across the board, the temperatures also show relatively good agreement. In some cases, the temperatures are higher or lower. These are predominantly due to heat transfer coefficients that are slightly incorrectly predicted or slightly different between Flownex and CFX. But again, across the board, we see relatively good agreement, not only in the trend, but also in the absolute values. In this example here, we see about 6.5 Kelvin difference on average across all of the different film cooling holes. Next, Mark will show how these results from Flownex are incorporated in external flow models in CFX and what differences can be seen in the external flow results as well.
Thank you, Vincent. And now I would like to present you some comparisons of the results of the simulation runs with the injection region model. All the plots shown the adiabatic wall temperature at this vane surface. The results are presented within a matrix. The left column presents the results which were generated using the cooling inflow conditions provided by the fully resolved Ansys CFX model. And the right column shows the results of the inflow conditions provided by the Flownex 1D network model. In addition to that, the matrix rows show the influence of the mesh resolution on the results. The upper row presents the results of the model where all the cooling hole patches were resolved by the surface mesh, and the lower one shows the results using the hexagonal arrow mesh. As you can see, if you compare the different columns, the results with the cooling inflow boundary conditions of the fully resolved model on the left-hand side agrees pretty good with the results of the inflow conditions given by the Flownex 1D network model on the right-hand side. The temperature distribution agrees very well, and hotspots are predicted close to be the same. If you compare the results of the different rows, you can recognize the effect of the mesh resolution. Of course, if the whole patches are resolved, the surface temperature is predicted cooler, as the cooling flow will be more mixed out with the main flow. Whereas with the arrow mesh, the cooling streaks can be seen more evident, as the cooling flow is just injected in a few cells. But this is expected. An additional comparison was done for the streamlines coming out of the cooling holes. Once again, the streamline pattern of the simulation, which is using the inflow conditions of the fully resolved model, compares very well with that one using the boundary conditions provided by the Flownex 1D network model. As expected, the finer the mesh, the more detailed the flow structures of individual cooling jets can be recognized. Therefore, the upper row shows more distinct cooling jet structures, even if only every fourth streamline was used for the visualization. So let's conclude our talk. The Ansys injection region model is a reduced order approach which allows to model film cooling in the early design phase. In our presentation, we showed you a first successful coupling of a 1D network model from Flownex with Ansys CFX for film cooling. Flownex was used to provide the inflow conditions for each film cooling hole and slot, respectively, and coupled to the film cooling model in Ansys CFX. The shown approach offers a potential for better and faster prediction of the influence of the film cooling flow on the aerodynamics of the turbine blades in the early design phase. And last but not least, sure, we will continue to evolve and improve the modeling and the coupling approach itself.